So let's jump right into the second video on the principle of least action. But I have to make a quick correction here on my signage. I had a minus here. This should really be a plus, and this should be a minus. And we can see that because mxn is a positive term. This guy's positive, and the other two are negative. So we can see how I made a bit of a mistake there. What we're going to do now is we're going to develop this term out further. First, we're going to need a bit of a mathematical trick, as we've seen sometimes with these derivations. And this is going to be very similar to the integration by parts derivation, if you've ever seen that one. So if you take a time derivative, or any variable really, if you take a derivative of two functions, f and g, you apply the chain rule and you get f dg by dt plus g df by dt. Okay. If you multiply both sides by dt and then integrate, so I'm just going to copy and drag this out a bit, so I have to rewrite all that, you will get a relationship. So integrate, multiply both sides by dt. I'm not going to worry about constant integration because eventually we're going to be matching up with this, and we have endpoints t1 and t2. Okay, so this first part boils down to just fg, and then the other two integrals remain, but I'm going to rewrite them slightly. I'm going to write them as fg dot dt plus gf dot dt. Now, to match with this thing up here in red that I've drawn, I'm going to say let f equal mx bar dot, and g is going to be just eta. So rewriting this, okay, we're going to rewrite this. Let's use a different color. Let's use, say, white. We're going to rewrite this. We're going to get fg, which is mx bar dot eta, equals the integral of mx bar dot and eta dot dt. Now, we do have to be a little bit careful. Okay, so this is actually going to be evaluated from eta t2, eta t1. Can't forget that. And this integral goes from t1 to t2. And then we get a plus integral of g, which is eta times f dot, which is mx bar double dot, which demonstrates the convenience of using the dot notation. Okay, so t1, t2. Now I'm gonna point out an observation here. This term here, eta at t1, eta at t2. Let's redraw our scenario. We have t1 here, and then this path, which I would call the real path, t2. And then this squirrely thing that we're saying could be theoretically possible. But what we're going to do is at these points, okay, at t1, t2, I'm going to pin the error to 0. So I'm going to say n at t1 equals n at t2, which equals 0. And you might say this is by definition, but you might also, sorry, this is x and t. You might also say that this is what sort of pins this to reality. And I'm saying at the endpoints it has to match. Otherwise, this is not even representative of our physical system. So this being true actually puts this to 0. Okay, so now we have this expression that we can derive for this thing. So the integral t1, t2 on mx bar dot eta dot dt, we can say equals the negative of this guy, equals negative t1, t2, eta, so let me scooch this over a bit, equals eta times mx bar double dot dt. Now remember, this is only part of our equation up here. Let's try not to forget this piece. And what I'm going to say is that in the limiting case, let's see if we can get all this in here. In the limiting case, ds goes to 0. So I'm going to have to try to argue, and if we take the integral of what we just defined, t1, t2, eta mx bar double dot dt, and then minus integral t1, t2, and then just copying this one here, x bar, and then eta dt. We have to say that this equals 0. Okay, this is what we're trying to show, that this thing goes to 0. So we can do a little bit of factoring. We're going to take the negative outside. The negative actually goes away, but we'll draw it anyways. Let's use a different color. Let's use orange. So if we take the negative out, and then T1, T2, the eta also comes out, and then you get mx bar double dot plus the potential function, the derivative of the potential function, evaluated at x dot, okay, times dt equals 0. So now we pose the question, which portion of this integral must be 0 to cause the whole thing to collapse? And I'm going to argue that in this theoretical framework, eta is not 0, okay? I'm going to argue that this is not equal 0 based on how we've defined it. We can see that there is some error here. It may be small, but I'm even theoretically saying that there's some deviation in that flight path, as I've called it. Okay, maybe I'll draw that a little thicker. Right? There's error here. Okay, so now you will assert, or you must assert, that this thing equals 0. So let's do that. And of course, this is where you get the fascinating result. You get EP prime x bar equals negative mx bar double dot. Okay, if you look really closely, you're going to see that this is the partial differential of the energy with respect to, say, x bar equals negative m, and well, what's x bar double dot? It's a bar. And what was this bar term? This bar term was what actually happens in reality. So this is quite interesting. If you recall from the first video, I told you that we can get rid of the bars. Okay, we can get rid of the bars. I told you that the partial of energy with respect to energy with respect to position equals negative p dot. Or the other way around, you can say p dot. Let's do it the other way around. P dot is equal to the negative of that. So now I'm asserting from these two statements that p dot equals ma. Well, we're going to give this a name, and we're going to call this force. So this is Newton's law, one of Newton's laws, F equals ma. And it seems to have sort of come up in this derivation of principle of least action. What we can further show here is that really what this is defining, and if you remember back to our first video, I just kind of tucked it away and I said define P is equal to mv. Well, we don't need to define it anymore. Because when you take the time derivative of P and set it equal to the time derivative of mv, you will notice that the fact that P equals mv is resultant from this derivation. It is resultant. So in my mind, this is sort of, I think it's an incredible result. I think it's an incredible theoretical result that, of course, aligns with our observations about energy and momentum. But now we are saying something more fundamental. And from the inverse square law, I told you sort of arbitrarily that the acceleration is going to equal the negative gravitation constant times the source divided by r squared. With this new definition of force that we've now sort of derived, we can say F equals ma, okay? And we can say that this equals to mg, or it's more commonly written gm, lowercase m over r squared. And what's the point of all this? It seems like, okay, well, we already knew all this. What's the point of this? What we're saying is that, what I'm showing you is that originally, this quantity here, originally when I derived it, it was arbitrary. When I derived the inverse square law, I said that there's a source and there's some source field for the gravity, and it yields an inverse square law if it radiates outward in the way that we would expect. And this acceleration didn't have meaning, but now it has meaning. Okay, so now I'm saying, I'm first told you it was acceleration, And now from this derivation, I've now confirmed my suspicion that momentum equals mass times velocity in our sort of observed reality. So what I'm saying is that this is not arbitrary. This is not an arbitrary statement. And in fact, the acceleration of a Newtonian body really does follow this inverse square law. I mean, to the best of our knowledge, if you were to go through the rigors of defining this, this is what you land on. You have to imagine a time where you didn't have instruments accurate enough to see exactly what the flight paths of these celestial bodies were. And you could chart them out and you had data, and you think of the times of Kepler and Newton, they had data. But you have to remember in the 1600s, there was argument as to whether, planets orbited the sun in circles or how that worked. The data was there, they couldn't fit it to a model. And what I'm suggesting to you is that this model, which Kepler and Newton both found, is that it was purely based on logic. It was purely based on sort of this rhetoric surrounding these principles. And sort of scrolling back to the top here, I'm reminding myself why I'm doing these videos. The principles I've described to you so far are basically, there are things that have fields that radiate. There are sources involved with those fields. I've now shown you by a principle of least action that nature operates in this sort of minimum principle. In our graph here on the left, nature is going to take x bar. It's not going to take theoretical x. There is an x bar that it takes that is minimized. I'm telling you that that sort of momentum equals mass times velocity. That is a result of the principle of least action. And from that, you can deduce that the force then is equal to the mass times the acceleration. And Newton's laws and how Newton defined them, he tells us that force and acceleration have this relationship. Therefore, this acceleration, this inverse square law, describing this acceleration is not arbitrary and stands up to the rigor of this logic. So I'm going to do some more videos soon. We're going to get into ellipses and elliptical orbits. And then angular momentum, of course, is of enormous importance. But I wanted to do this video first to say that the fact that the acceleration of a body follows an inverse square law is not arbitrary. That was the point of this video, was to describe a rigorous logic that shows it's not in fact arbitrary. And this concept and this theory, it aligns with experiment. So that's how we know that it's true. Now, of course, there's an asterisk there, because, well, what happened? We found out that there was, I believe it was a moon that was orbiting around Jupiter, Titan, I think. And the precession of this elliptical orbit over time was basically deviating from Newton's laws. And what they had found was that this body was rotating so quickly around the planet and was so far from Earth that relativistic sort of principles kicked in, and you had to apply this adjustment factor that relativity accounts for. So that's a bit of a different story, but we can kind of put ourselves in the minds of Kepler and Newton and realize they didn't have the tools to discern these very tiny errors, and that this theory that they produced regarding the inverse square law in elliptical orbits was phenomenally successful in predicting the orbits of celestial bodies. Anyways, that's all I have to say on the principle of least action. So like and subscribe, and hope to catch you next time.